Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillahirrabbilalamin. All praises to Allah who give us opportunity and good health so we can gather in this seminar. We hope that this pandemic will come to an end very soon. First of all, let me introduce myself. My name is Zakaria. On this occasion, I'd like to present my research about PI and PI anti-wind-up speed control of switch reluctance motor. I am from School of Electrical Engineering and Informatics, Institute Technology Bandung. This is our team in this research. These are the overview of my presentation. The first one is introduction. The second is controller design. The third is simulation results. The fourth is results and discussion. And the last one is the conclusion. The introduction section. What is electric vehicle? As we can see in this electric vehicle block diagram, the electric vehicle is a vehicle that consists of battery as energy source, an electric motor that drives the wheels, and then the controller that regulates the flow of energy from the battery to the motor. There are three types of motor that used on electric vehicle. The first one is PMSM, and the second one is induction motor, and the third one is switch reluctance motor. On previous research, there are 9 required features of electric motors for electric vehicle. These are the features, and the 3 most important features for electric vehicle are weight, fault tolerance operation, and reliability. Based on that 3 features, SRM has better performance compared to PMSM and induction motor. This is the SRM testbed that we use in this research. The blue line is the SRM and the mechanical load. The red line is the SRM driver and the controller based on Arduino Uno, and the low pass filter RC to rectify the PWM signal. And the green line is the batteries, and then this is the speed sensor and the speed encoder with 96 volts that installed in the SRM gear. This is the SRM specification. The control input to the SRM driver is between 0.8 to 5 volts. And then when we test, the SRM rotates at an input voltage between 72 to 84 PWM values. So the control output value must be between 72 to 84 PWM. And the resulting control signal is only a positive control signal. The system modeling is done by black box method because we don't know the parameter of the SRM. We don't know about the value of resistance or the value of inductance. The modeling is done by providing control input and measuring the output. The output is the rotational speed. This is the picture of SRM, and then this is the driver of SRM, and this is the, let me zoom, this is the input saturation that we must follow when we control the SRM. Why we choose PI and PI anti-wind-up control strategy to control the speed of SRM. Why PI controller? SRM is a highly nonlinear system. The nonlinear control strategy is done such as sliding mode control, fuzzy controller, or adaptive control to achieve the high dynamic performance of SRM. That control strategy need the accurate model of the SRM, but the accurate SRM models are difficult to build. The PI controller has the advantage of controlling unknown object models. And the second reason is the PID controller is the most controller used in industry. The most used PID combination is PI controller. So why we choose the PI controller? We wind up because in PI controller there is saturation. It is possible that the control signal that appears exceeds this range. So the PI anti-wind up is chosen to overcome that possibility. This is the SRM open loop block diagram, and then how to determine the SRM linear operating points. A nonlinear system can be linearized at its operating points. The behavior of a nonlinear system around the operating points can be approximated by assuming that the system is linear, but shouldn't move too far from its operating point. We test the SRM in an open loop, then we measure the response. The response is rotational speed. This is the open loop test results. The x-axis is PWM and the y-axis is RPM. And this is the operating points that we use to design the control system. The purpose of this research is to design the SRM speed control with saturation and nonlinearity constraints in SRM by linear approach. Now let's go to the controller design section. The next step is define the SRM transfer function. The SRM transfer function is defined by these steps. Okay, as you can see, this is the data of PWM versus RPM. In 800 RPM, the data is like this, and then we input the data into sysid MATLAB, and then we get the transfer function of order 1. This is the SRM open loop transfer function. This is the open loop system response of SRM model. The rise time, the settling time, the overshoot, the undershoot, and the peak time. To determine the Kp and Ki values, it is done analytically with the criteria of 2% and the desired settling time is 0.1 second, and the steady state error is 0%, and the overshoot is plus minus 2%. And this is the step to determine the proportional gain and integral gain. And the diagram block is like this picture with Ks, with the system is like this. Okay, and after we calculate the proportional gain and integral gain, we get the proportional gain is 0.03 and the integral gain is 36.11. Next to the simulation results, and this is the continuous time PI simulation. This is the discrete time PI simulation. The change from continuous to discrete domain using zero order hold method with time sampling 20 milliseconds. Okay, this is the system, and this is the system response and the control signal, and this is the specification of the response. And then this is the PI simulation, anti-wind-up continuous time. This is PI anti-wind-up simulation in discrete time. And now let's go to the results and discussion. This is the implementation of PI controller. This is the SRM response, and this is the control signal. Okay, now the implementation of PI anti-wind-up controller. The system response is like this picture. Let me zoom. The system response is better than PI controller. The PI anti-wind-up is better, as we can see. And this is the control signal. And now it's the data tabulation about the system response compared to open loop response of SRM. Okay, as you can see, the last part of this presentation is the conclusion. This research has succeeded in implementing an SRM speed control system with PI and PI anti-wind-up controllers. The relationship between PWM and SRM speed is non-linear. In this study, a linear approach was used. The approach is carried out around the SRM operating point, which is 800 RPM. After the designed control system is implemented, the system is able to track the given set point. During testing, the system response graph from both motors were obtained and divided into 4 areas or 4 zones, namely area 1, area 2, area 3, area 4, and area 5. Each controller is able to provide a response that is not too good and has not been able to meet the desired specification in the set point area that is far from the operating point. This happens because of the nonlinearity of the system. Okay, I think this is the end of my presentation. Thank you for your attention. I apologize if there is a mistake. Wassalamualaikum warahmatullahi wabarakatuh.